We all know about light, light sources, and behavior of light. The science that deals with the behavior of light is known as photonics. Photonics is the physical science of light and application of light generation, detection, and manipulation through emission, transmission, modulation, sensing, and signal processing as well. To perform all these manipulation actions and also to know the behavior of light, one has to know about different concepts of light, natures of light, as well as different theories of optics. We have four different optic theories known to be ray, wave, electromagnetic, and quantum optics. Now, ray optics comes into the picture when the light propagates through and around objects whose dimensions are much greater than the wavelength of light. In our daily life, we can observe this that the objects around us reflect the visible light or sunlight at different wavelengths, and this comes into the concept of ray optics because those objects are having the dimensions much greater than the wavelength of light. We can observe another thing that those objects appear in different colors because they reflect, every object reflect light at different wavelengths of light, so that we can observe the change in the appearance of color. And we can say that ray optics is the simplest theory of light. According to this, light is described by rays that travel in different optical media in accordance with set of geometrical rules. Ray optics is concerned with the location and direction of rays. It is therefore useful in the studying of. In the concept of ray optics, we have two different laws, the law of reflection and the law of refraction. Law of reflection. Light reflects from mirrors in accordance with the law of reflection. It says that the reflected ray lies in the plane of incidence and the angle of reflection denoted by theta r equals the angle of incidence theta I, which we can observe from the below images. In the first image, we are trying to incident a ray onto the mirror, and the mirror is reflecting the light. That we can observe that here the reflected ray is in the same plane of incidence, and we can observe from the second image that we are trying to incident light ray at an angle of 30 degrees, and here we are getting reflection also at 30 degrees. Now, law of refraction. It is also known as Snell's law. At the boundary between two media of different refractive indices N1 and N2, an incident ray is split into two rays. One is a reflected ray and other is a refracted ray. According to this, the refracted ray lies in the plane of incidence, and the angle of refraction theta 2 is related to the angle of incidence theta 1 by Snell's law, as n1 sine theta 1 is equal to n2 sine theta 2. In the below image, the image 1, we can observe the incident ray here is splitted into two rays. One is a reflected ray and other is a refracted ray. When we are trying to incident a light ray from a rarer medium to a denser medium, then the light ray bends towards the normal to the surface. An important extension of Snell's law is the concept of total internal reflection and critical angle. If a ray is incident in a medium of higher refractive index with the angle of refraction greater than the angle of incidence, the refracted ray bends toward the boundary. here in the image we are trying to incident a light wave at the boundary between two media with the different refractive indices. Here the theta1 is the angle of incidence, and we can observe that the light ray is getting refracted with an angle of theta2. In the other case, we are increasing the angle of incidence, and the light is getting refracted at 90 degrees. For internal refraction, theta2 should be greater than theta1, so that as theta1 increases, initially theta2 reaches to 90 degrees. This occurs when the angle of incidence is equal to the critical angle theta c. If we apply Snell's law at the boundary between two media with different refractive indices, then we can have n1 sine theta c is equal to n2 sine pi by 2, that is equal to n2. Here to demonstrate the concept of internal refraction, we are considering the angle of incidence as theta c, critical angle, and the refracted angle at 90 degrees. So we'll get the critical angle as sine inverse n2 by n1. When theta 2, that means when theta 1, the angle of incidence is greater than the critical angle, Snell's law cannot be satisfied, and there will be no refraction taking place. The incident ray will be totally reflected back into the medium as if the surface like a perfect mirror. This phenomena is called total internal reflection. The total internal reflection is the basis of many optical devices and systems, such as reflecting prisms and optical fibers. Fiber optics. An optical fiber is a cylindrical waveguide made of a low loss material such as silica glass. It has central core in which the light is guided, embedded in an outer cladding of a slightly lower refractive index. The light ray incident on the core cladding interface at angles greater than the critical angle undergo total internal reflection, and they are guided through the core without refracting into the cladding. And we have different parameters for optical fiber, out of which now we'll consider one parameter, that numerical aperture. By applying Snell's law at the air core boundary, we can have 1 into sine theta a is equal to n1 into sine theta t. From the image we can observe that we are trying to incident light ray at air core boundary. That means the refractive index of air is 1, so we are taking n1 as 1 according to Snell's law, and we are trying to incident the light ray at an angle theta a, so that 1 into sine theta a is equal to n1 into sine theta t. Now sine theta a that will give n1 cos theta c. According to the concept of critical angle and total internal reflection, the sine theta a will become n1 into root 1 minus n2 by n1 whole square. That will give us as sine theta a is equal to under root n1 square minus n2 square. That we will consider as numerical aperture. That means numerical aperture of an optical fiber is the under root of n1 square minus n2 square. Now from that the acceptance angle can be derived as theta a is equal to sine inverse of numerical aperture, or sine inverse of under root n1 square minus n2 square. The acceptance angle theta a of the fiber determines the cone of external rays that are guided by the fiber. Light rays incident at angles greater than theta a are refracted into the fiber but guided only for a shorter distance, since they do not undergo total internal reflection. The acceptance angle thus is a crucial design parameter for coupling light into and out of the fiber. The numerical aperture therefore describes the light gathering capacity of the fiber. Modes of fiber. Fibers with constant refractive indices in the core and the cladding are known as step index fibers. When the core diameter is small, only a single mode is supported, and the fibers with smaller core diameter are known as single mode fibers. Fibers with large core diameters are said to be multimode fibers, thus resulting in modal dispersion. Modal dispersion means there will be distortion in the transmission of light in the optical fiber. This modal dispersion can be reduced by grading the refractive index of fiber core from a maximum value at its center to a minimum value at the core cladding boundary. The fiber is then called as graded index fiber or GRIN fiber. The number of modes of an optical fiber is given by m is equal to 4v square by pi square, where v refers to the another parameter of optical fiber known as fiber v parameter. Now, V parameter. Fiber V parameter is an important parameter that governs the number of modes of the fiber and their as well as their propagation constants. It can be calculated as V is equal to 2 pi A by lambda naught into Na, or pi d by lambda naught into Na, where Na is the numerical aperture of the optical fiber. Therefore, we can say that V is directly proportional to the core diameter to wavelength ratio and as well as the numerical aperture of the fiber. Now, it's optical waveguides. A medium of refractive index N1 embedded in a medium of lower refractive index N2 that is lesser than N1 acts as light trap within which optical rays remains confined by multiple total internal reflections at the boundaries. An optical waveguide is a light conduit consisting of slab, strip, or cylinder shape of dielectric material embedded in another dielectric material of lower refractive index. The light is transported through the inner medium without radiating into the surrounding medium. Based on the concept of optical waveguides, integrated optics technology has been evolved similar to the integrated circuit technology in electronics, where various optical components and devices are combined on a single substrate, in which optical waveguides provide the links among those optical components and devices. And we can classify the optical waveguides into two major categories: one planar mirror waveguides and other is planar dielectric waveguides. We can have different geometries of, that means different structures of waveguides, like embedded strip and a strip, as we can observe here. Another is a rib type, and one we can have a strip loaded structure of optical waveguide. We can have different shapes of optical waveguides or different configurations of optical waveguides, like straight strip. Another is a S bend, that means the inner medium of optical waveguide will be in the form of S shape, S bend. Another we can have Y branch. Another is a Mach Zehnder configuration, like that. And we can use different materials to construct optical waveguides. Some of them are titanium embedded in a lithium niobate, and here in this structure of optical waveguide, the blue color medium, that is having higher refractive index, this is the inner medium, and this is the outer medium. So the main material, like titanium embedded in lithium niobate, the titanium will be in the middle, and it is surrounded by lithium niobate. As like we can say that the inner medium is a core of optical fiber. Similar to optical fiber, it is a core and it is cladding, like that. We can say the optical fiber has two different materials with different refractive indices. The other majorly used optical waveguide material is silica in silicon. Next, wave optics. Wave optics theory is useful when the light propagates through and around objects whose dimensions are close to the wavelength of light. According to the wave optics, light propagates in the form of waves and in a free space with a constant speed of c is equal to 3 into 10 power 8 meter per second. Now, wave equation. An optical wave is described by a real function of position or of x, y, z and time, because the wave varies with respect to time. This is denoted by u of r comma t, which is known as wave function, and it satisfies a partial differential equation called as wave equation. The wave equation can be given as del square u minus 1 by c square into dou square u by dou t square is equal to 0. And we have another wave equation called Helmholtz equation. That means this Helmholtz wave equation is given in complex plane, whereas this wave equation is given for Cartesian plane. The Helmholtz equation is given for complex plane. So if we want to represent the wave equation in complex plane, we have to transform from the Cartesian plane to the complex plane. So as we said above, u of x, y, z comma t, that means the wave function to be represented in the complex plane as u of xyz. With the complex plane means we have to get complex terms. That means we have to represent time, the time of wave in complex terms like this. And to transform Cartesian plane into the complex plane, we consider j omega as dou by dou t. So it yields dou square by dou t square as minus omega square. If we substitute this in the wave equation, that means del square u minus 1 by c square into minus omega square u is equal to 0. That yields del square u plus omega square by c square u is equal to 0. So now we represent omega by c with a constant k, then we will have del square u plus k square u is equal to 0. This is known as Helmholtz equation, where the constant k represents a wave number that is given by omega by c. Now, diffraction of light. Optical wave transmission through aperture leads to the diffraction of light. When an optical wave is transmitted through an aperture in an opaque screen and travels some distance in free space, its intensity distribution is called the diffraction pattern. Based on the concept of diffraction, we have certain components known as diffraction gratings. A thin transparent plate with periodically varying thickness serves as a diffraction grating. It splits an incident plane wave into multiple plane waves traveling in different directions. Let us consider a diffraction grating made of thin transparent plate placed in the z is equal to 0 plane, that is xy plane, whose thickness varies periodically in the x direction with a certain period. This plate converts an incident plane wave traveling at small angles theta I with respect to the z-axis into several plane waves at small angles with respect to the z-axis. The diffracted angles are given as theta q is equal to theta I plus q into lambda by the period of diffraction grating, where q represents the order of diffraction. When the diffracted angles are very large, then the sign ratio of diffracted angles comes into the picture. Since the angles theta q depend on the wavelength of light, an incident polychromatic wave is separated by the grating into its spectral components. A diffraction grating directs two waves of different wavelengths lambda 1 and lambda 2 into two different directions with angles theta 1 and theta 2. The diffraction grating therefore serves as a filter and as well as used in spectroscopy. Now, the concept of interference. When two or more optical waves are simultaneously present in the same region of space and time, the total wave function is the sum of individual wave functions. When two monochromatic waves with complex amplitudes u1 of r and u2 of r are interfered, the result is a monochromatic wave of the same frequency with complex amplitude u is equal to u1 plus u2. Based on the phase difference of the two waves or two or more waves, we can have constructive or destructive interference. The intensity of the total wave is given as u is equal to I is equal to u square. This we can write like this, and we can from this we can yield the equation of interference like this, where phi denotes the phase difference. That means the difference between the phase of two different waves. If the intensities of both waves are equal, then as I naught, then the total intensity of the total wave is 4 I naught cos square phi by 2. When this phase difference between the two monochromatic waves is 0, the total intensity is 4 times the intensity of superposed waves, and we can have maximum interference. When the phase difference is pi, on the other hand, the superposed waves cancels and interference cancels out, and the total intensity is 0. Based on the concept of interference, there has been the development of different devices known as interferometers. An interferometer is an optical instrument that splits a wave into two waves using a beam splitter, delays them by unequal distances, redirects them using mirrors, and recombines them using another beam splitter or the same beam splitter, and detects the intensity of their superposition. We have four important interferometers. One is Mach-Zehnder interferometer, Michelson interferometer, Sagnac interferometer, and Fabry-Perot interferometer. One by one, we'll look into those instruments. The first one, the Michelson interferometer. Michelson interferometer is an optical instrument that splits a wave into two waves using a beam splitter, delays them by unequal distances, redirects them using mirrors, and recombines them using the same beam splitter, and finally detects the intensity of their superposition. As we can observe here in the image, let us say this is a wave u0. This wave u0 is split into two waves u1 and u2, and they are directed to different mirrors. After traveling in different paths, the waves are the waves are redirected by the mirrors and recombined by the same beam splitter, and they are traveling to the detector, where the intensity of the superposition of the two different waves can be recorded. The main application of Michelson interferometer is an optical coherence tomography. Next, Mach-Zehnder interferometer. Mach-Zehnder interferometer splits a wave into two using a beam splitter, and delays them by unequal distances and redirects them using mirrors, recombines those beams using another beam splitter, and detects the intensity of their superposition. As it has two different paths for light propagation, it can be used for detecting the phase difference of light wave as well as the intensity matching. Light is divided at a beam splitter into two paths with one light path containing a sample and other is acting as a reference path. The higher refractive index of the sample changes the phase of the light in that path, so that constructive or destructive interference occurs upon the beam recombination at the second beam splitter. This in turn modulates the light intensity at the photodetector, which then can be used to determine the difference of refractive index between sample and reference. It is generally used along with the other optical devices like optical waveguides, which detects the phase difference between two waves, which is given by delta phi is equal to 2 pi by lambda into delta n effective into L, where lambda represents the operating wavelength, n effective represents the refractive index of propagation mode of waveguide, and L is the length of sensing arm of Mach-Zehnder interferometer. The Mach-Zehnder interferometer can also be used as thermo-optic switches, sensors, and as well as used in spectrum analyzers. The other is Sagnac interferometer. Sagnac interferometer splits a wave into two waves using a beam splitter, delays them by unequal distances, redirects them using mirrors, and recombines them using the same beam splitter, and detects intensity of their superposition. In Sagnac interferometer, the splitted, that means the light ray incident at the beam splitter, that is splitted into two waves, the splitted light waves as well as the reflected beams propagate in the same path with opposite direction. Sagnac effect pertains to the relative phase shift between two beams of light that travel on an identical path in opposite direction within a rotating frame. Its principle is based on an optical path difference induced by counter propagation of beams in a rotating frame that is proportional to the rotation. Sagnac interferometer finds application as the modern day fiber optic gyroscopes used for navigation purposes, allowing highly accurate measurements of rotation down to 10 power minus 4 to 10 power minus 5 degrees per hour. Another is Fabry-Perot interferometer. Fabry-Perot interferometer is made up of two parallel highly reflective mirrors that transmit light only at specific uniformly spaced frequencies, which depend on the optical path length between the mirrors. We can say that it is a folded Michelson interferometer because interference in Michelson interferometer can be understood in terms of thin film interference. Let us imagine that the arms of Michelson interferometer are rotated, as we earlier observed that we have two different mirrors at two different lengths. If we rotate, that means if we rotate the mirrors of Michelson interferometer such that there is a single optical axis as shown in this figure. In Fabry-Perot interferometer, interference occurs due to the multiple superpositions of both reflected and transmitted beams at the two parallel reflectors, so that we can give the equation for phase difference in Fabry-Perot interferometer of the phase difference of superposed waves in superposed beams in Fabry-Perot interferometer as 2 pi by lambda into n into 2L. The Fabry-Perot interferometer may be used as a sharply tuned optical fiber or a spectrum analyzer. It can be used as an optical resonator for laser, sensor, and the operation of Fabry-Perot controller, Fabry-Perot interferometer is controlled by varying the path length. That means by varying the distance between reflecting mirrors. Now we come to the concept of electromagnetic optics. The concepts of ray optics and wave optics are not able to explain the transmission of light through a certain medium. When a fraction of light transmitted through a medium, it turns out to depend on the polarization of the incident light. Hence, the light has to be treated as a vector quantity comprising of electric field and magnetic field, which vary in time and space, leading to the concept of electromagnetic optics. The electromagnetic wave is nothing but we can consider a natural light. In general, along with radio waves, X-rays and gamma rays, the natural light is electromagnetic phenomena that is described by vector wave theory. In the electromagnetic spectrum, optical frequencies ranges from the infrared through the visible to the ultraviolet region. We can characterize electromagnetic radiation by the equation E is equal to h nu, that is equal to hc by lambda. In the electromagnetic wave, the two fields are mutually perpendicular to each other, and the electromagnetic wave propagation is perpendicular to both fields, as we can observe in this image. The electric field and the magnetic field are mutually perpendicular, and the direction of electromagnetic wave is perpendicular to both the fields. An electromagnetic wave is An electromagnetic field is described by two related vector fields that are the functions of time and space, which are electric field and magnetic field vectors. Here we can observe the set of equations, four equations. They are interrelated and satisfy the set of coupled partial differential equations known as Maxwell's equations, using which we can describe the electromagnetic waves of light. That means we can say that change in the electric field produces the change in magnetic field, or change in the electric field produces magnetic field, and as well as change in magnetic field produces electric field. The necessary condition for electric field and magnetic field to satisfy Maxwell's equations is that the each component, that means the each of the electric and magnetic field components should satisfy the wave equation of light. That is, we know that del square u minus 1 by c naught square into dou square u by dou t square is equal to 0, the wave equation. If we substitute electric field in place of u, we can characterize the electric field wave, and if we substitute h, if we try h there, then we can get the magnetic field wave. Upon solving those electric field and magnetic field equations, we can finally derive the speed of light as c naught is equal to 1 by under root epsilon naught into mu naught, which can be approximated as 3 into 10 power 8 meter per second. And let us consider a medium with no free electric charges. There we come across with two additional vector fields, electric flux density and magnetic flux density. Then the four fields E, H, D, B are related by Maxwell's equations in a source-free medium, like we have here with two different parameters, new parameters, electric flux density and magnetic flux density. Now, polarization. Electromagnetic waves are transverse waves in which movement of particles is perpendicular to the direction of the wave. Light is the interaction of electric and magnetic fields traveling through the space. These two fields move in different planes that are perpendicular to each other. As shown in the figure, the left part of the polarizing filter is unpolarized light, that is comprising of electric field in one plane and magnetic field in another plane. Those two are perpendicular to each other. The light wave that is vibrating in more than one plane is known as unpolarized light. And in the right part of the filter, polarizing filter, we can observe the light wave propagating only in one plane. This is the polarized wave. The polarized waves are light waves in which vibrations occurs in single plane. The process of transforming unpolarized light into polarized light is known as polarization. We can have different types of polarization. The polarization of the light at a fixed position is determined by the time course of the electric field vector. uh, we can have the electric field equation like this. When the phase difference between the two components, then we can have the linear polarization of the wave. And when the phase difference between the two electric and magnetic fields is plus or minus pi by 2, and electric field components of x direction and y direction are equal, then we can have circular polarization. For any other phase differences, we can say that it is elliptically polarized light. Now we have an optical device called wave retarder. Wave retarder alters the polarization state of a light wave traveling through it. The wave retarder transforms the component of the wave and then delays the y component of the electric field wave by some phase. When this phase is pi by 2, it is known as quarter wave retarder. And it converts linearly polarized light wave into left circular wave and right circular wave into linearly polarized wave. When the phase of y component of electric field wave is pi, then the wave retarder acts as a half wave retarder. This transforms linearly polarized light wave into another linearly polarized wave with plane rotation, and left circularly polarized wave into right circularly polarized wave. While the wave retarder transform one form of the polarization into another form, polarization rotator always maintains the linear polarization of light wave, but the plane of the plane of polarization will be rotated with a certain angle. The polarization rotator converts linearly polarized wave into another linearly polarized light wave by rotating the plane of polarization by certain angle. Now let us go to the concept of quantum optics. Although electromagnetic optics provides the most complete treatment of light, it fails to account certain optical phenomena like absorption, fluorescence, and photoelectric effect. These phenomena are described by the quantum version of electromagnetic theory known as quantum optics. From a quantum perspective, light consists of certain particles called as photons. A photon carries electromagnetic energy and momentum as well as intrinsic angular momentum. The photon has zero rest mass and travels at a speed of light in vacuum, and in matter with a reduced speed, let us consider c, that is less than the actual speed of light. Photon optics provides that the energy of an electromagnetic mode with the discrete energy levels separated by the energy of a photon. The energy of a photon is given by E is equal to h nu, where h is a Planck's constant, and in terms of electron volts, the energy of a photon is given by 1.24 by lambda naught, where lambda is the wavelength of light. Now the concept of interaction of photons with atoms, that with matter. According to atomic theory, an atom may emit or absorb a photon by undergoing upward or downward transition between its energy levels, conserving energy in terms of photons. Let us consider the energy levels of an atom E1 and E2 and frequency of photon nu. The energy of photon with which is interacting with atom matches the energy level difference is given by h nu naught is equal to E2 minus E1. During the interaction of photon with atoms, we may come across with the three following phenomena: absorption, spontaneous emission, and stimulated emission. Absorption. Absorption of a photon of energy h nu leads to an upward transition of an electron in atom from energy level 1 to the energy level 2. That means electron from ground level is transported to the higher energy level. Then spontaneous emission. If the electron in an atom is initially in upper energy level, it may decay spontaneously to the lower energy level and release its energy in the form of a photon with energy h nu is equal to E2 minus E1. Another thing is stimulated emission. Stimulated emission occurs when the electron in the excited level interacts with another photon with energy E2 minus E1, producing a clone photon. As a result, two photons get emitted. The quantum optics find many useful applications, out of which spectroscopy is very important, which is based on either absorption or fluorescence. Now, absorption spectroscopy. It is useful for the characterization of materials. It uses the wavelength dependent absorption characteristics of materials to identify and quantify specific substances. Absorption spectroscopy is based on the measurement of transmittance or absorbance of light by the sample. The transmittance and absorbance are given as the transmittance T is equal to I by I naught and absorbance A is equal to log of I naught by I. This I naught is represent incident and transmitted radiations. I naught and I represent incident and transmitted radiations. The concept of absorption is explained by Beer-Lambert's law, which gives absorbance A is equal to epsilon BC, where epsilon is molar absorptivity, P is path length of sample container, and C is molar concentration of sample. Here, in the concept of absorption spectroscopy, we have two different spectrophotometers. One is a single beam spectrophotometer and other is a double beam spectrophotometer. A spectrophotometer consists of light source, a monochromator, and this is for wavelength selection, and a sample cell, and then a photodetector, from that amplifier and a readout. In a single beam instrument, light from monochromator passes through the sample cell and detected by the photodetector. From here, the absorbance or transmittance is directly calculated and displayed on the displayed in several ways. Most of the modern spectrophotometers are based on double beam spectrophotometer design. In a double beam spectrophotometer instrument, two beams are formed by a beam splitter. One beam passes through the sample path and other passes through the reference path. In a double beam instrument, two beams are formed by the beam splitter. One beam passes through the reference solution to a photodetector and the second simultaneously traverses to the sample to the second or matched detector. The two outputs are amplified and their ratio is determined and displayed by the digital readout device. The double beam design lends itself well to the continuous recording of transmittance or absorption spectra. This has become basic for the development of UV visible spectrometer. This instrument has one more additional arrangement of concave grating from the double beam spectrophotometer, using which the radiation is dispersed, and it also focuses the beam on a rotating sector mirror. This instrument has a wavelength range of 200 to 2000 nanometer. Now, fluorescence. Fluorescence is the emission of light by a substance that has absorbed light. In the context of fluorescence, the emitted light has longer wavelength than the absorbed radiation, which results in less photon energy. We can also say that fluorescence is a phenomena that a material emits light at one wavelength while we illuminate at it another wavelength. In general, fluorescence is a very fast process. We can say that the time of fluorescence, that means nanosecond decay times, but some special fluorophores have longer decay times in terms of micro or milliseconds, second decay times, based on the concept of phosphorescence. This can be used to improve signal to noise ratio. We can easily understand the difference between fluorescence and phosphorescence, as in fluorescence a material lights up when it is exposed to light or ultraviolet radiation. When we turn off the light, the fluorescence stops well. In phosphorescence, material lights up when exposed to radiation, and when we turn off the light, the phosphorescent material keeps glowing until it slowly fades out to dark. This is due to the emission of photon from singlet excited state to the triplet excited state for certain materials, which acts as a metastable state, where the photon energy is logged for some time. To reach ground state, there is a requirement of additional energy provided by the photons. This may take time delay, which makes the process slower than the fluorescence. Fluorescence spectroscopy finds application in various fields, it is used in biochemical fields, medical, chemical research for analyzing organic compounds, and used in differentiating different skin tumors, used to identify the concentration of dissolved substances in a solution, and fluorescence well known used for field water research by detecting dissolved components and dissolved contents, oxygen or organic pollutants, and heavy metal particles in the water. Laser. Laser is a special device that is based on the concept of quantum optics. Laser is a device that emits light through optical amplification based on the stimulated emission of electromagnetic radiation. Stimulated emission allows a photon to induce an atom whose electrons in upper energy level to undergo transition to lower energy level with the emission of clone photon. These two photons in turn serve to stimulate the emission of two additional photons, and so on, while preserving the properties of laser. Ordinary light sources emit light with different wavelengths, and for wave trains with different wavelengths, the phase difference changes naturally. Ordinary light does not radiate in parallel directions, but it travels in different directions. Unlike natural light, laser light is a highly directional, monochromatic, and coherent light source. Laser is composed of discrete electromagnetic waves that are both temporally and spatially coherent. Also, we can observe a fixed phase relationship in both propagation and perpendicular direction, which makes it monochromatic. The laser is an optical oscillator. It comprises a resonant optical cavity and a resonant optical amplifier whose output is fed back to the input with matching phase. The laser is an optical oscillator in which the amplifier serves as active medium. Frequency selection is jointly achieved by the resonant amplifier and the resonator, which admits only certain modes. Output coupling is accomplished by making one of the resonator mirrors partially transmitting. And we have two basic lasers, out of which one is neodymium doped yttrium vanadate laser. Here the neodymium is doped into the material called yttrium vanadate. These lasers often incorporate interactivity doubling crystals. When frequency is doubled, the transition provides a green emission at 532 nanometer. It is most common laser, finds applications in medicine, biophysics, automotive industry, military, and cavity ring down spectroscopy. Now, ruby laser. Ruby is the first material in which laser action was observed. Ruby, that is chromium doped in aluminum oxide, is a sapphire aluminum oxide material in which chromium ions replace a small percentage of aluminum ions. Together with the flash lamp, ruby rod is enclosed in a reflecting cylinder of elliptical cross section. It is a three-level laser system. Level 1 is the ground state. Level 2 comprises a pair of closely spaced discrete levels correspond to the red laser transition at the wavelength of 694.3 nanometer. The level 3 comprises of two broadbands centered about 550 nanometer green light and 400 nanometer violet light. These absorption bands are responsible for the emission of reddish color of the material as it passes through these energy levels, as the material passes through these energy bands. In the excited state, that is at level 3, a fraction of aluminum ions get replaced with chromium ions. The excited chromium ions rapidly decay to the level 2, which is a metastable state where those electrons stay for a longer duration. After that, by spontaneous emission, they reach level 1, which takes longer duration to emit a reddish color at 694 nanometer wavelength. Now we are going to discuss about a few applications of photonics in terms of different optoelectronic devices and as well as photon manipulation. That means in terms of optical modulation. The concepts of photonics and electronics together give rise to the new concept of semiconductor optoelectronic devices, where photons produce charge carriers and the generation and the flow of photons is governed by the charge carriers. Semiconductor optoelectronic devices serve as photon sources like LED and laser diode, and they also used as amplifiers, detectors, waveguides, and sensors, etc. Semiconductor materials absorb and emit photons by undergoing transitions among allowed energy levels. For any semiconductor optoelectronic device, two processes are fundamental. The absorption of photon creates electron hole pair. The resulting charge carriers alter the electrical properties of the semiconductor. This process is basic for the operation of photodetectors. The another is the recombination of electron hole results in the emission of photon. This process is responsible for the operation of semiconductor photon sources. The spontaneous process is responsible for the generation of photon in light emitting diode, whereas stimulated process is basic for laser diode operation. Now, light emitting diode. An LED is just like a normal PN junction diode but with light emitting properties. The LED works when it is forward biased as like a PN junction diode. When it is forward biased, the potential barrier gets reduced and the electrons and holes combine across the depletion layer. As a result of light or photons, light or photons are emitted in all directions. A semiconductor material emits light as a result of electron hole recombination. An external source of energy can be used to produce electron hole pairs in sufficient numbers so that they produce large amount of spontaneous recombination radiation, causing the material to glow or luminescence. An LED is a forward biased PN junction fabricated from a direct bandgap semiconductor material that emits light through injection electroluminescence. LED is a forward biased PN junction with a large radiative recombination rate arising from injected minority carriers. Considering the physical structure of LED, normally PN junction of LED is encapsulated in a dome-shaped transparent case so that light is uniformly emitted in all directions and to have minimum internal reflection to avoid reabsorption of emitted photons. Often for different purposes, LEDs are encased in transparent epoxy lenses to achieve emission in all directions with various patterns. Let us observe in the image A with no lens, B with hemispherical lens, C with parabolic lens covering the junction of LED. Based on different types of lens used, we can observe different patterns of light coming out of the device. Epoxy lenses enhance the extraction efficiency. A lens with a refractive index close to that of a semiconductor optimizes the extraction of light from the semiconductor into the epoxy. Encapsulation protects the semiconductor chip, increases light extraction by reducing refractive index mismatch and serve as a lens to shape the beam. The shape and size of the epoxy lens can be altered so as to maximize the extraction of light at the epoxy air interface. If we come to the materials of LED, they are the combination of third and fifth group elements. Example like gallium arsenide, indium gallium arsenic phosphate, etc. Gallium arsenide was the first such material to be fabricated in the form of an LED and a laser diode. Photon sources fabricated from third, fifth group semiconductors offer long times, unlike those make use of second and sixth group alloys. Considering the configuration, LED may be constructed either in surface emitting or edge emitting configurations. The surface emitting LEDs emit light from the face of device that is parallel to the plane of active region. These are used in optical fiber communication. Whereas the edge emitting LED emits light from the edge of the active region used for telecommunication purpose. With the combination of third, fifth group semiconductors, high brightness light is readily generated at all colors of the rainbow from the ultraviolet to infrared region. To get various colors in LED, different combinations of materials is used for different spectral wavelength. If we have a direct band gap gallium arsenide semiconductor LED, we can get IR light using aluminum addition, UV light using indium, and using gallium arsenic phosphate. It is possible to get red, yellow, or orange color light. Forward bias PN junction diode can be operated as a light emitting diode, semiconductor optical amplifier, and as well as a laser diode. The difference we can observe that if we apply an external voltage across the PN junction diode, we can get photon emission, which is considered as LED. Now, if we try to pass photon energy through the PN junction, we can get amplified output used as semiconductor optical amplifier. Whereas with the feedback between semiconductor materials, the PN junction diode emits photon by spontaneous or stimulated emission similar to laser, named as a laser diode. Now, a photodetector. A photodetector is a device that measures photon flux or optical power by converting the energy of the absorbed photons into the measurable form. There are two principal types of photodetectors are in practical use. One is photoelectric detector and other is photothermal detector. The operation of photoelectric detector is based on the photoelectric effect. The absorption of photons by a material causes electrons to transition from lower energy level to higher energy levels, resulting in mobile charge carriers. Under the effect of an electric field, these carriers move and produce a measurable electric current. The photo effect takes two forms. One is external and other is internal. The external photo effect involves photoelectric emission, in which photo generated electrons escape from the material as a free electron, like in the production of X-rays. The internal photo effect involves photoconductivity, in which the excited carriers remain within the material and serve to increase the conductivity of the material. The other class of photodetectors is thermal detectors. They operate by converting photon energy into heat. As they require time to respond to a temperature change, thermal detectors are generally inefficient and slow in comparison with photoelectric detectors. Due to the recent advancements in manufacturing and miniaturization of thermal detectors, they are now viable contenders for imaging applications in infrared region, especially in medical field. Now we arrive at phototubes. Photodetectors of class photoelectric emission can have the form of vacuum tubes called vacuum photodiodes or phototubes. In figure A, we can observe a single vacuum phototube, and in B, electron multiplication, making it as a photomultiplier tube. Electrons are emitted from the surface of photocathode and travel to anode, maintained at higher electric potential. The photocathode can be opaque and operate in reflection mode, as like in figure A, or semi-transparent, or operate in transmission mode like in figure B. As a result, the electron transport between cathode and anode, a current proportional to the photon flux is created in the circuit, known as a photocurrent. The photo emitted electrons may also create a cascade of electrons through the secondary emission, leading to the development of a very sensitive device called photomultiplier tube. The secondary emission occurs when the photo electrons impact other spatially spaced semiconductor in the tube called diodes, which are maintained successively higher potentials similar to the anode. As a result, there is a huge amplification of generated photocurrent by a factor of 10 power 8. A photomultiplier tube can be used to detect and count individual photons. It is an extremely sensitive device and it is an extremely sensitive detector of light in UV, visible and near IR ranges. It offers large dynamic range. However, it is bulky and requires high voltage supply. Now, photoconductors. The absorption of a photon by an intrinsic semiconductor results in the generation of free electron excited from the valence band to the conduction band, along with the generated hole in the valence band. The application of an electric field to such material results in the transport of both electrons and holes through the material, producing an electric current in the circuit. Photons absorbed in the depletion layer generated electrons and holes, which are subjected to the local electric field within the layer. The two carriers drift in opposite directions. This transport process induces an electric current in external circuit. The electrical conductivity of the material increases in proportional to the photon flux. An electric field applied to the material by an external voltage source causes electrons and holes to be transported. This results in a measurable electric current in the circuit. It finds applications a photoresistor when it is used in electric circuit. In the electric circuit, it acts as a resistor whose resistance depends on photon intensity, making it as a photoresistor. Now, photodiode. A photodiode is of a p-ion structure or p-n junction. When a photon of sufficient energy strikes the diode, it creates an electron-hole pair. If the absorption occurs in the junction's depletion layer or one diffusion length away from it, these carriers are swept from the junction by the built-in electric field of the depletion region. So, by applying a high reverse bias, holes move toward the anode and electrons move toward the cathode, and a photocurrent is produced. The disadvantage of the p-n junction photodiode is that the depletion width is very small and depends on the doping concentration of the semiconductor. This can be overcome by using p-ion photocathode, which is a special case of p-n junction photodiode. A p-ion diode is a special p-n junction with an intrinsic layer sandwiched between p and n layers. The result is increasing of the width of the depletion layer of the device. This increases the area available for the capturing of light. In the intrinsic region of the the number of electrons is equal to the number of holes. Once the flooded electrons and the holes reach an equilibrium point, the diode will conduct current. The advantage of p-ion structure is the quantum efficiency and sensitivity. The gain of the device can be controlled by the thickness of the intrinsic region, while a thin p and n regions can be maintained. Some photodetectors incorporate internal gain mechanisms so that the photocurrent can be amplified by carrier multiplication within the detector. This makes a signal more easily detectable. If the detection layer electric field is increased by applying reverse bias across the junction, the electrons and holes generated the electrons and holes generated may themselves acquire sufficient energy to liberate additional electrons and holes within the layer. The devices in which this internal amplification process occurs are known as avalanche photodiodes. Now, the camera and the relation of camera to the photodetector. The primary component of a camera is the optical sensor. The optical sensor contains up to millions of discrete photodetector sites called as pixels. All modern day cameras can be categorized as charge coupled devices and complementary metal oxide semiconductor imagers. In a camera system, the image sensor receives the incident light in the form of photons that is focused through the lens. Depending on whether the sensor is CCD or CMOS, it will transfer the information to the next stage either as voltage or digital signal. CMOS sensors convert photons into electrons, then to a voltage, and then into a digital value using an on-chip analog to digital converter, then stored as digital image data. Now, CCD sensors. CCD sensors start and stop exposure for all pixels at the same time. This is known as global shutter. The CCD then transfers this exposure charge to the horizontal shift resistor, where it is then sent to the amplifier, and then the image data is stored in digital format. the CMOS sensors. Earlier, CMOS sensors were only able to start and stop exposure one pixel row at a time, which is known as rolling shutter. This has changed over time by developing modern global shutter CMOS sensors. CMOS sensors are smaller ADCs for each pixel column, allowing for high frame rates than CCDs. CMOS sensors are advantageous compared to CCDs for image quality, image speed, and dynamic range. Now we go to the concept of manipulation of photons. This manipulation can be achieved by optical modulators. Optical modulators are the widely used photon manipulators for which the light energy is supplied in the form of photon beams. An optical modulator is a device which is used to modulate the intensity, phase, wavelength, and polarization of light beam. All these actions are performed with light photons only by passing the light through a medium with different refractive index from the input light, or with some devices like diffraction grating or polarizer, etc. Here in the diagram, we are trying to pass light through a medium with equal refractive index of the incident light, and we can observe the change in intensity or amplitude of the wave due to the absorption of light by the medium. If we have higher refractive index of the medium, we can observe the phase change of the light beam. Sometimes we can see the change in amplitude and phase simultaneously in the last case. These optical modulators are broadly classified into the two categories of absorptive modulators and refractive modulators. Absorptive modulator is what we can transform continuous wave light into discrete type based on the absorption of modulator. In refractive modulators, we have electro-optic and acousto-optic modulator. This electro-optic modulators correspond to phase modulation, amplitude modulation, as well as polarization. Now we are here with the acousto-optic modulator. In acousto-optic modulator, the refractive index of an optical medium is altered by the presence of sound. Sound therefore modifies the effect of the medium on light. When the periodic acoustic field is applied to the medium where light is transmitting, the actual light transmission gets deflected. Sound comprises of compression and rarefaction pattern. When it is in compression mode, the density of the optical medium is higher with the higher refractive index. When it is at a rarefaction, the density of the medium is very less, and resulting in lower refractive index of the material. Many useful devices make use of acousto-optic effect, including optical modulators, switches, deflectors, filters, isolators, and frequency selectors, as well as spectrum analyzers. Now, electro-optic modulator. Electro-optic modulator, in which a refractive index of the material is changed by the help of applied electric field to the optical medium or material. It is related to the modulation of phase, amplitude, as well as polarization. If the refractive index changes in proportional to the applied electric field, the effect is known as linear optoelectric effect or Pockels effect. The change in the refractive index is given by the following equation, where this tau represents Pockels coefficient. In case if the refractive index changes in proportion to the square of the applied electric field, then the effect is known as quadratic electro optic effect or Kerr effect. The change in the refractive index is given by the following equation, where this coefficient S denotes the Kerr coefficient. Thank you.